Welcome to AI Podcast. Today we're digging into a NeurIPS 2025 paper called Model Provenance Testing for Large Language Models.
Catchy title. Give me the quick takeaway first. What's the big idea?
In a sentence, it's a practical black box way to tell if one language model is derived from another. Like a fine-tuned child from a parent, using only API access and some statistics.
So, no peeking at the weights or secret training data, just how the model behaves when you talk to it?
Exactly. Think of it like family resemblance testing. You show both models the same prompts and ask, do they tend to start their answers the same way more often than unrelated models do?
When you say start their answers, you mean the first word or token, right?
Right. They focus on the next token, basically the first step in the model's response. It's a coarse signal, but it turns out to be very informative.
Who's behind this work?
The team includes Ivica Nikolic from the National University of Singapore and Teodora Baluta from Georgia Tech, among others.
Got it. Why do we need this in the first place? What problem are they solving?
The field is flooded with fine-tuned variants. Companies need to enforce licenses, researchers need to trace vulnerabilities, and everyone wants to know whether a deployed model is a lightly tweaked version of something else. But many models are API only, so traditional fingerprinting or watermarking doesn't apply.
I remember watermarking schemes that modify training or rely on hidden signals. How is this different?
Those approaches often require changing the training process or having white box access. This paper treats models as black boxes, no training changes, no internal peaks. Just ask questions and compare behavior.
Okay, walk me through the test itself. What do they actually do with the prompts?
They collect a bunch of short, natural prompts, feed them to the suspected child model and the suspected parent, and record how often the first token matches. Then they compare that match rate to the match rates between the child and a whole lineup of unrelated control models.
Like asking, does this kid resemble the alleged parent more than any random person in the crowd?
Exactly, and they use a standard multiple comparisons procedure, the Bonferroni method, to make sure they're not fooling themselves by cherry picking.
Nice. Where do the prompts come from?
They generate them automatically, think incomplete sentences and everyday fragments, and they keep them short to make the test efficient over an API.
Why does the first token carry so much signal? Isn't that too simple?
It's simple on purpose. The first token reflects the model's learned priors before the conversation diverges. If a child is fine-tuned from a parent, that first step often stays similar. It's like the opening move in chess revealing a player's style.
And the controls are crucial here, right? Without them, you might misread general stylistic overlap as provenance.
Exactly. The control pool anchors what random similarity looks like. If the alleged parent similarity stands out compared to those controls, that's evidence of derivation.
What did they use for evaluation? I'm curious about the data sets and the setup.
2 benchmarks. One is a carefully curated set where they know the parent-child pairs with high confidence. The other is a large, diverse collection mined from public model hubs. That second one is closer to the messy real world.
And the results?
On the curated benchmark, precision lands in the high 90s with solid recall. On the larger, more varied benchmark, precision stays strong but recall drops, which makes sense because there's more noise and domain variation.
Let's unpack that a bit. High precision means when the test says yes, it's almost always right. Lower recall means it sometimes misses true parent-child pairs.
Exactly. If you're using this for license enforcement, you'd rather be very sure about the positives, even if you miss some. If you're doing forensic analysis and want to find every possible derivative, you might accept lower precision and push recall up by using more prompts.
Speaking of prompts, how many do they need?
About 1,000 per model is a nice sweet spot for the full test, but they also propose tricks to cut costs.
Such as?
One is prompt rejection sampling. You probe prompts offline on the parent and controls, and you keep the ones that look more informative. Another is a best arm identification strategy, a bandit-style way to reduce how many times you query the larger set of reference models.
So you spend your budget where it matters most. I like that. How well do those cost savers hold up?
The rejection sampling preserves a lot of the signal with far fewer queries. The banded approach saves offline compute, but can hurt recall if you get too aggressive. It's a trade-off.
What about the scenario where you already suspect a specific parent? Does that change the game?
It helps a lot. If you come in with a named parent candidate, precision gets even better because it's harder for the wrong parent to look like the best match by chance.
Any assumptions I should be aware of? For example, what if someone tries to game the test?
Good question. The threat model here is mostly non-adaptive. If an adversary fine-tunes specifically to avoid matching first tokens or adds noise to the opening word, they might lower detectability. The paper flags that as a direction for future work.
So it's not an arms race solution yet, but it's a solid baseline. What about limitations beyond adversaries?
A few. First, using just the first token is a deliberately coarse measure. It travels well across APIs, but richer signals like short n-grams or log probabilities could help. Second, performance depends on the quality and diversity of the control set, especially for niche domains like medical or code. Third, the ground truth labels in the large benchmark can be noisy, which makes evaluation tougher.
And scale? Did they test frontier-sized models?
Most of the models are in the small to mid-range. The method should scale in principle, but the paper calls for more work at the top end and across languages and modalities.
What about openness? Is this something people can try today?
Yes, they released code and benchmarks so teams can reproduce the results or adapt the tester to their own model pools.
I'm thinking about practical use cases. Let's say a company finds a nasty bug in their base model. How does this help?
You can quickly scan deployed models to see which ones are likely descendants, then prioritize patches or advisories. Same for license compliance. If your model shows up embedded in a product, you can test whether it's derived without needing a subpoena for weights.
That's useful. Still, I can hear someone saying, what if two unrelated models trained on similar data happen to behave alike on those opening words?
That's why the controls matter. If the crowd of unrelated models shows similar match rates, the test won't call provenance. The alleged parent has to stand out from that background.
Right. And if it doesn't, you either need more prompts, better controls, or a richer signal.
Exactly. It's like turning up the exposure on a camera. If the picture is washed out, you need to adjust the lighting, not guess what was there.
I'm curious about the statistics for a second. Home Bonferroni sounds intimidating. How would you explain it at a coffee table?
Imagine you're making several yes or no calls at once. Each call can be fooled by random chance. Home Bonferroni is a disciplined way to set the bar a little higher across all those calls so your overall false alarm rate stays low.
Nice. So stepping back, what's the headline contribution here?
A simple, black box protocol that works with real-world APIs, backed by statistics, and validated on realistic benchmarks. It turns the vague question of who your model is from into an operational test.
And your favorite caveat?
Don't forget the controls and don't overinterpret a single signal. If the stakes are high, combine this with other evidence like metadata, training disclosures, or more granular behavioral tests.
Future directions, then? What would you like to see next?
Adversarial robustness is big. Also, blending first token matching with small n-gram or log prob signals, and better automated ways to assemble domain-matched control pools, and of course, multilingual and multimodal extensions.
My pick would be policy integration. Clear playbooks for how organizations use this during audits or incident response, so decisions don't hinge on one engineer's hunch.
Absolutely. Tools are only as good as the processes around them.
All right, let's land the plane. What should listeners remember?
Provenance isn't mystical. With enough carefully chosen prompts and a solid control set, you can make a strong, statistically grounded call about whether a model is a derivative, all through an API.
And while it's not a silver bullet, it's a practical step forward for licensing, safety, and accountability in the model supply chain.
That's the show. Thanks for listening to AI Podcast.
See you next time.